Let us first talk about an experiment in physics because it asks the question this whole video is about. Can you look at something without changing it? A man sets up an experiment, a source that fires particles one at a time, a barrier with two slits cut in it, and a screen behind it. He fires them for an hour and on the screen he gets stripes, which is not what you'd expect because stripes are what waves make. Each particle has somehow gone through both slits, so he does the obvious thing. He puts a detector at the slits to see which one each particle really takes. The stripes disappear. He gets two plain bands, which is what you'd expect from something that had to pick a side. Then he switches the detector off. The stripes come back. Nothing was pushed and nothing was touched. The only thing that changed was whether the answer could be known, and that was enough to change the answer. Everything anyone knows about whether these machines are safe comes from watching them do things. So that is a strange fact about particles, and it is an ordinary fact about machines we are building today. And it is already happening. In OpenAI's most recent report, there are two numbers on GPT-5.6. 1 in 2000 and 56 in 100. They are the same measurement of the same model, counting the same thing. One was taken while the model was doing ordinary work, the other while it sat a test. And what they count is how often the model, thinking out loud, notices that it is being tested. On the test, it noticed more than half the time. In ordinary use, almost never. So it is about 1,000 times more likely to notice it is being watched when it is actually being watched. And that gap is the reassuring number here. It should not be. The report is the GPT 5.6 system card published on the 9th of July. About 80 pages of test results. Section 7.4, page 28. OpenAI calls the behavior metagaming. Their own definition is plain enough. It is when a model reasons about how it will be graded or watched rather than about the problem in front of it. Think of a student who stops working out the answers and starts working out what the examiner wants to see. So how would you measure that? You would have to read its mind. So they read its working instead. These models write out their thinking before they answer, and the second model reads that and flags it. Which means the whole measurement rests on one thing. It only ever counts what the model wrote down. And here's why that matters. Nobody has ever measured how often people cheat, because you cannot. What a survey measures is how often people cheat and then admit it. Two things multiplied together. How often it happens, and how often they admit it. If 100 people cheat and half of them admit it, your survey says 50. But if 200 people cheat and only a quarter admit it, your survey still records 50. Same answer, twice the cheating. The survey cannot tell those two worlds apart, and neither can you. Now, hold on to that, because one number in OpenAI's newest report is built exactly this way, and it just moved. That is the situation here. The flagged rate is how often the model does it times how often it says so. One number, two unknowns, and you do not get to solve that. So when the number moves, you have learned that the answer changed. You have not learned which one moved. One more thing, because you should be asking it, how do we know that the flagger is any good? A flagger has two jobs: catch the real cases and stay quiet on the clean ones. A lazy flagger can ace the first job. Just flag everything and you have caught everything there is. Average the two jobs and the lazy flagger scores 50 out of 100. It sounds like it is at least trying. So they do not average. They multiply the two and take the square root, and a machine that just says yes to everything scores 0. Because anything times nothing is nothing. You cannot pass by doing only one job. And now the turn. Because the report hands us the missing piece twice, pointing opposite ways. One of the tests checks whether the coding model wrecks a user's files while it is busy doing something else. And on that one, GPT 5.6 scored far higher than the model before it, much more visible, much easier to catch. And here's OpenAI's own explanation, printed in the card. This indicates increased observability, not necessarily increased incidence. In plain words, It did not start doing it more. It started describing it more. Now the other direction. A second test asks whether the model gets swayed when a user hints at the answer they are hoping for. And on that one, GPT 5.6 scored lower, harder to catch. And the reason, again in the card. The older model would say out loud that the user's suggestion had swayed it. The newer one simply does not mention it. Nobody saw that the swaying stopped. What stopped was the mention. So one score went up because the model started talking, and the other went down because it stopped. Neither of them is about behavior. Which brings us back to the number that went down. Across its own training, on OpenAI's honesty tests, the flag rate fell from about 70 in 100 to about 55. Down 14 points. On the face of it, a model doing it less. Progress. But we have just taken this number apart. It is two things multiplied. So which one fell? Try it. So suppose the model became a third less likely to write the thought down. Then for the measured number to land exactly where it landed, the behavior underneath has to have gone up by about a fifth. Same fall, and underneath it more of the thing, not less. I'm not telling you that this is what happened, and nobody can tell you that. That's the point. But two other numbers in the same section lean that way. The report also measures how well a model can deliberately reshape its own working when told to. They want that number low. Their words are that it is an early warning sign of models getting better at shaping or hiding their reasoning. It went from 4 in 1,000 to 13 in 1,000, roughly 3 times better at hiding. And when they measured the flag rate on training data instead of on the tests, it did not fall. It drifted up. 3 numbers. The one that gets reported went down. The 2 that measure whether we can still see went the wrong way. And 1 number survives all of it. It is none of these 3. Now finally the honest catches, and there are 3 of them. First, the test where the model noticed most was built out of impossible tasks, jobs that cannot actually be done. An impossible task may simply make the model realize it is being tested, that is not skimming, it is being sharp. Second, some of these test setups held only 2 to 5 real cases. The card says so itself and calls the result highly uncertain. Small numbers move easily. Third, they checked whether the flagger was catching something harmless, like the model quoting a safety rule back to itself. They report that this was not the cause in almost all of them. So take all 3 catches seriously. 1 number still stands. In 23 of every 100 answers on that honesty test, the graders judged that noticing the test had changed what the model did. That is not a model failing a test. That is a test that has stopped working. There is one more detail and it is easy to miss. To find out whether a model can hide its reasoning, they give it instructions to follow. One of those instructions was to write the words that is not suspicious at the beginning and the end of its own working. That is the one instruction they left out of the published results, for technical reasons. So back to where we started. 1 in 2000 out in the world. 56 in 100 on the test. The gap was the reassuring number. It is the same fact from the other side. Now let's go back to the slits for a second. Every number in that report was taken with the detector on. There is no other kind of number because there is no way to test a model without testing it. An electron is not trying to fool anybody. It does not know that you are there. Ours somehow does, more than half the time, and it writes it down. There is something very old about ending up here. The Greeks worked at this for 300 years, and the most careful of them finished by saying that they did not know. They treated that as something you had to earn. We are walking back to the same place from the other side. Not by thinking too carefully, but by building faster than we can check. They arrived at not understanding and called it wisdom. We are going to arrive at it and call it progress. So the question is not whether these things are safe. It is whether safe is still a thing we can measure. So, how safe is something that knows when you're trying to understand it? If that was useful and you want more like this, please consider subscribing.